This is Unit 10, Lesson 3. We are going to look at the pH scale and acid-base indicators today. Okay, so basically the intention for today is to use the pH scale and acid-base indicators to basically tell how acidic or how basic a solution is. All right, so let's start off with the do now. Remember, pause the video here, try out these questions, and then unpause me. Okay, so what do you already know about the pH scale? You probably said something about measuring acid or something to do with acids and bases, obviously, because we're in that unit. Maybe you've seen on like water bottles, sometimes they give the pH of the water inside, right? I know that some brands advertise their basic solution with a pH of like 8 or something like that. But yeah, so number 2 here says, and this is a review question, we have an equilibrium expression here. Okay, we have water in equilibrium with hydrogen ions and hydroxide ions. Okay, remember what this means, right? Water is turning into H plus and OH minus at the same rate that H plus and OH minus are combining to form water. So remember, this would look like nothing's happening, but in reality, we know the forward and reverse reaction are equal in terms of the rate. So according to Le Chatelier's principle, if the concentration of hydroxide, right here, ions is increased in this expression, what will happen to the concentration of H plus? So remember, if I increase the concentration of something, it's going to shift the reaction away from that side. So if I add more OH minus, it's going to make more water. And the only way I can take OH minus and make water is to use up some H plus. Okay, so by shifting to the left, okay, so we're adding OH minus, shifting to the left, we're going to decrease the concentrations of everything on the right. Okay, so that means H plus, the concentration will decrease. All right, so if I have this system at equilibrium, I have a certain concentration of H plus, and I add more OH minus, it's going to combine with that H plus to make water, and I'm going to have less H plus left over. Okay, so the answer here is B, decrease. H plus will decrease. Okay, that's going to be important today. All right, so let's start off by talking about the pH scale. So, excuse me. Over on the right here, we got the entire pH scale. It goes from 0 to 14. Okay, 7 being neutral or pure water, right? This is pure water with nothing dissolved in it. And then what we're going to see is, well, let's go through this. So the pH scale is developed as a measure of concentration of H plus ions. Okay, so it's all about measuring the concentration of H plus ions. The more H plus, the more acidic, right? Like we have like soda is an acidic solution, and it has many more H plus ions than OH minus. Okay, something like oven cleaner is a very basic solution, and it has very few H plus ions compared to OH minus. Okay, and then water is a perfect balance. It has equal parts H plus and OH minus. Yeah, as you can see depicted in these pictures here. Okay, so it's really, the pH scale is about, it's measuring the concentration of H plus ions. So sometimes you're going to see H plus written as H3O plus, which is called hydronium. It's the same thing, okay? Same thing. H plus and H3O plus is the same thing, okay? So, and it's just, and in terms of, you know, it doesn't look like the same thing, right? So there's different ways to write acids and the ions they contribute, right? So when H plus is donated to water, it can combine with H2O and make H3O plus, or it can exist as H plus ions. So for our purposes, these are the exact same thing, okay? So you could also say the pH scale was developed as a measure of the concentration of H3O plus ions in a solution, okay? So this is super important. An increase of 1 on the pH scale, so if I'm going from 9 to 10 or 10 to 11 or 0 to 1, an increase of 1 means it's 10 times less acidic. Okay, so the smaller the pH, the more acidic it is. So and it's a logarithmic scale. Okay, which means if I go from 4 to 5, that means I just got 10 times less acidic. Or I could say I have 10 times less H plus or H3O plus. I could also say it's 10 times more basic. All right, so lots of ways to say the same thing. So you have to know how to change between them. Okay, so if I'm going from, and you can pick any jump, from 5 to 6. Going from 5 to 6, so going from black coffee to saliva, for example, right? Um, right, we could say that saliva is 10 times less acidic than coffee. Or we could say saliva has 10 times less H plus ions, or H3O plus, than coffee. Or we could say saliva is 10 times more basic than coffee. Okay? So a couple key things to remember here. Each step is 10 times more. So one step is 10 times, 2 steps is 100 times, right? 10 times 10. 3 steps is 1,000, then 10,000, then 100,000, and so on, right? So you're just adding those zeros. So that's important. And you also have to remember that the lower values are more acidic and the higher values are more basic, right? So a pH of like 1 is very acidic. Okay, and a pH of like 13 or 14 is very basic, all right? And both of those things are dangerous, by the way. Okay, so if an increase of 1 is 10 times less acidic, that means a decrease of 1 is 10 times more acidic, or 10 times more H plus or H3O plus, or another way to say that is it's 10 times less basic. So if I'm going from tomatoes down to like Coca-Cola, okay, so that's going from a pH of 4 to a pH of 3. Okay, so Coca-Cola is 10 times more acidic than tomatoes. It has 10 times more H plus ions, or H3O plus ions, than tomatoes. Okay, and Coca-Cola is 10 times less basic. Okay, all those mean the same thing. All right. I would recommend pausing here because this is super important. This is like crucial to understand for the pH scale. Make sure you have it straight because it's easy to flip it around. Okay, so every step is 10 times. Okay, and if you're getting smaller on the pH scale, you're getting more acidic, and if you're getting larger on the pH scale, you're getting less acidic. But there's different ways to say that, right? So more acidic, you could also say there's more H plus. You could also say less basic. All right, so make sure you have those straightened out before you move on. This is just, so I have here is just it broken down by ways you can describe different solutions. So we generally say low pHs are strongly acidic. 3 to 5 or 3 to 6 is moderate to weakly acidic. 7 is neutral. It's not acidic or basic. All right, and then once you get above 7, you're starting to get basic. So 8 is a little basic. 9, 10, 11 is moderately basic. And then 12 to 14 is very strong base. Okay? So here's some more examples. Tomatoes are 1,000 times more acidic than pure water. Sounds intense, right? And you know tomatoes like, really? Because I bite into a tomato and it doesn't like burn me. Yeah, it's not so acidic, right? I mean, if we think about, it does have a little, you can taste it, right? You can taste that if you think of a citrus fruit or something too. You can taste that acid. It's like a little bit sour. But so if we look, right, pure water is 7, tomatoes are 4. So look it, I'm taking 1, 2, 3 steps down. So I'm taking 3 steps toward the more acidic side. And for each step I take, you add a 0, right? So 7, 1, 2, 3, down to 4. That's 3 steps, 3 zeros, 1,000 times more acidic. And you have to pay attention to what direction you're moving. Because I could also say, oh, pure water is 1, 2, 3, 1,000 times more basic than tomatoes, right? So there's kind of a phrasing that you have to pay attention to as well. Okay. Stomach acid, which is HCl, all the way down here, is 100,000 times more acidic than pure water. Now that is a lot, right? And that will cause damage. Okay, it's very acidic. So, right, if we look, that's 7 down to 0. Hold on, 1, 2, 3, 4, 5, 6. I think, yeah, hydrochloric acid is really a pH of 1. Apparently on here it says 0. So if we go by this scale, it's actually a million times more acidic, right? Because that's 1 step, 2, 3, 4, 5, 6, 7, which means 7 zeros. Oh, I see. Okay, sorry guys. This is pure hydrochloric acid. Stomach acid is a 2 on the pH scale. Okay, so that's why I was getting confused there. So we're going from 7 to 2, which is 1, 2, 3, 4, 5 steps, 5 zeros, 1,000 times more acidic. Okay, that straightens that out. All right, one more example. Oven cleaner here, okay? 1 million times more basic than pure water. Well, let's check that out. 7, we go 1, 2, 3, 4, 5, 6 zeros, right? Take 6 steps, that means 6 zeros. Boom, 6 zeros. Oven cleaner, and we're moving in the basic direction, so oven cleaner is a million times more basic than pure water. Okay? You could also say that pure water is a million times more acidic than oven cleaner, right? It's kind of a weird way to say it, but you could say it that way. Okay? So let's do a couple of example problems here that you might be asked. So, a truck carrying concentrated nitric acid overturns and spills its contents. The acid drains into a nearby pond. The pH of the pond water was 8 before the spill. So originally it was 8. And then after the spill, the pond water becomes 1,000 times more acidic. What is the new pH of the pond water after the spill? Okay, feel free to pause the video and try it yourself. So if we're starting off at 8, okay, and we're getting 1,000 times more acidic, so acidic means I'm going down the pH scale, right? The number's going to get smaller. And remember that each step is 10 times, or like you can think about the number of zeros. So 1,000 times that's 3 zeros, that's 3 steps toward the acidic side. So I'm going from 8, 1, 2, 3, down to 5. Okay, so the new pH is going to be 5. All right? So 2 things you got to pay attention to, right? You're getting more acidic, so you have to be going in this direction, down. Hey, look, I know it's up on the picture, but down in terms of the number, right? And how many times, right, for each zero? So 10, 20, or not 20. I'm never going to give you something like that. It'll always be a multiple of, or a logarithmic, either 10, 100, 1,000, 10,000, etc. You can do in between those, but we're not going to deal with that. So 3 zeros means 3 steps, more acidic from 8, 1, 2, 3, that's a pH of 5. Okay, compare the hydronium ion concentration. So remember, hydronium, that's the H3O+, same idea as H+, okay? So compare the hydronium ion concentration between a solution of pH 4 and a solution of pH 10. So you can pause and try it yourself. So we have 4 here and we have 10 here. So, I mean, the difference, right, should be 6 steps. Okay, so 1, 2, 3, 4, 5, 6. So remember that the more acidic, the lower the pH and the more hydronium. So the pH of 4 has much more hydronium. Okay, so we can phrase this in a couple different ways. We could say there is, let's see, right, it was 6 steps, right? So 6 zeros means a million, right? So 1 with 6 zeros after it, that's a million. So we could say the pH of 10 is a million times less acidic, or we could say has a million times less hydronium ion concentration than pH 4, right? Because it is asking us to say hydronium ion to talk about that. So we could say, either we could say there's a million times more hydronium ions in pH of 4 compared to pH of 10, or we could say there's a million times less hydronium ions in a pH of 10 than a pH of 4. All right? So we know the difference is a million times, and then it's just about the phrasing, right? Remember that the 4 is more acidic, so you could say the pH of 4 has a million times more hydronium ions. But if you're talking about the pH of 10, you can say the pH of 10 has 1,000,000 times less hydronium ions. Okay? All right. So just remember that the more hydronium, or H plus, right? We could think about hydronium, which is H3O plus, is the same thing as H plus. The more of that you have, the more acidic it is. Okay? So pH of 4 has 1,000,000 times more hydronium ions than a pH of 10. All right. Okay, so that's one way. pH scale is one way to talk about how acidic or basic something is. Kind of a simpler way, and right, if you can't get in there and count all the H pluses, um, we have these things called acid-base indicators. Okay, these are chemicals that when you put them in a solution, they'll turn one color in a certain pH and a different color in another pH. Okay, so it's kind of a way to tell when a pH changes. Now, so you can see here, this table is also in your reference table. We got 6 different indicators, and the range is kind of where they're going to change colors or start to change. So the best use of these is outside of the range. So let me give you an example. Methyl orange, okay? It goes from red to yellow as the pH shifts in this range. So as you're going from 3.2 to 4.4, it's shifting from red to yellow, okay? So if it's a pH of 1, 2, or 3, it's going to be red. If it's a pH above 4.4, so 5, 6, 7, 8, 9, 10, 11, all those, it's going to be yellow, okay? So a common misconception here is it's actually methyl orange would be bad if you're trying to distinguish between two solutions that are in this range, right? Because if it's like a pH of 4, it's going to be kind of in between red and yellow, and that's why they call it methyl orange. It's going to be orangey, and that's not going to help us at all because we're not going to know if it's where it is in the range. So methyl orange would be good to test the difference between, say, a pH of 3, which is on the outside on this end, and a pH of 5. Okay? Because in a pH of 3, it's going to be red, and a pH of 5, it's going to be yellow. Okay? All right, one more little example. Let's do phenylphthalate. Right? It's a fun word. This one's actually really pretty when it's basic. Okay, so if you put phenylphthalein in a solution and it has a pH of either 1 all the way up to 8, well, all the way up to 8.2, right? It's going to be colorless, so you're not going to see it. Once you hit 8.2, it's going to start to turn pink. It's going to begin to turn pink, okay? Now, if you have a pH of 10 or higher, then the solution will turn pink, okay? So phenylphthalate would be good to distinguish between solutions that are, say, a pH of 5, which is below the range, and a pH of 11, which is above the range, okay? So I'm going to go through some example problems here that you would use this table for, okay? So number 1 says, based on the results of testing colorless solutions with indicators, which solution is the most acidic? All right, so that means we got to go through all of these, right? Okay, so 1 says a solution in which bromthymol blue is blue. So where's that? Bromthymol blue is here. So it looks like if it's blue, that means it's above 7.6. That's not very acidic at all. It's actually in the basic range. So it's probably not 1. Okay, unless all these other ones are way above that, which I don't think is going to happen. All right, so if a solution in which bromthymol blue is blue, that means the pH has to be above 7.6, right? It's on this end because it goes from yellow to blue. Okay, so let me just make a note of that. Right, so that means this has to be like 7.6 or higher, right, if it's going to be blue. That's a plus sign. Okay, so a solution in which, I can't say, bromcresol, I think, right, I never have to say these things, green is blue. Okay, so that's here, bromcresol, I'm not sure how to say that, to be totally honest. If this solution is blue, okay, that means it's above 5.4. right? It's on the right side of the range. So any solution that's 5, oh boy, point 0.4 or higher is going to be blue. So right now, we can get rid of answer 1, right? Because it's asking for the most acidic. So right now, this solution is the most acidic at a 5.4. Remember, the lower the number, the more acidic it is. Okay. Number 3 says a solution in which phenolphthalein is pink. All right, so if phenolphthalein is pink, it's on this end of the range. That means it has to have a pH of 10 or higher. All right, so 10 or higher, that's very basic. That's not acidic at all. Okay, so right now it looks like number 2 is going to be it because that's not right. But let's try the last one. A solution in which methyl orange is red. Oh, I think this is going to be it. So if methyl orange is red, that means it's on this end of the scale, so it's less than 3.2. So 3.2, or less. So this is the best answer here, because remember, it's asking for the most acidic. Okay. So if methyl orange is red, that means the solution has a pH below 3.2, which is pretty acidic. Okay, so that's going to be 4. All right, next one. Which indicator would best distinguish between a solution with a pH of 3.5 and a solution with a pH of 5.5? Okay, so the key to these types of questions is whatever the range is, you want these numbers to be outside the range on either side of it. Okay, so we're looking for an indicator where the range is between 3.5 and 5.5. So I think it's going to be this one right here, methyl orange. Oh, but that's not even an option, right? So methyl orange would be a good indicator. Oh, not really though, because 3.5 is in that range. Okay, so no, not methyl orange. So let's look at these then. 3.5 and 5.5. So bromthymol blue, 6. So a solution of 3.5 and 5.5 in bromthymol blue, both of those are going to be yellow, so that's not going to help. We're not going to be able to distinguish. So it's not that. I hate saying this one. Bromcrasol green, okay? That changes 3.8 to 3.5. Oh, you know what? This might be it. Because look, a pH of 3.5, this will turn yellow because it's on this end. 3.5 is over here. And a pH of 5.5 is on this end, and it's going to be blue. Yep, this is the right answer here. Okay, so again, this is the answer because it's asking which indicator would best distinguish between a solution with a pH of 3.5 and 5.5. So you want you want the indicator to be 2 different colors in each of these solutions. And we see that a 3.5 pH will be yellow, it's on this end, and a 5.5 pH will be blue, it's on this end. Okay, so that's going to help us distinguish between 2 different solutions of these pHs. All right, one more. Which indicator is blue in a solution that has a pH of 5.6? Okay, so again, I guess we're going to have to work through all of these. So bromcrasol green, pH of 5.6 will be blue. Oh, is that the answer again? That was easy, right? So 5.6, if we're looking at this one, is on this end, and it's blue. So I think that's the answer. Let's make sure, though, because I want to go through the other ones. So bromthymol blue, pH of 5.6. That's below the range. That's going to be yellow. All right, definitely not that one. 3, methyl orange. Well, first of all, methyl orange never even turns blue, so it can't be that, right? It's asking about blue in a pH of 5.6. And thymol blue, that's here. A pH of 5.6 is on this end, which means it'll be yellow. Okay, so yeah. So our answer is 1. All right. Now, I know this can be a little confusing, so definitely replay this. And I'll say one more time, right? Anything below the range, so below 3.2, below 6, below 8.2, below 5.5, anything below it will be this color. Anything above the range will be the other color. Okay, so if you want an indicator to tell you the difference between two pHs, the pHs have to be on either side of the range. So when you put the indicator in the solution, one of the solutions will turn, say, red, and the other will turn yellow, and then you can tell the difference, right? If I have a pH of 1, a solution with a pH of 1, and a solution with a pH of 2, both of those are going to be red if I add methyl orange to it, because they're both on this side of the range. So that's not going to help me at all, okay? So that's how you use these indicators. Okay, so of course, check for understanding. We've got a couple questions here and then a challenge question if you're feeling bold. Go ahead and pause and try these out, and I'll go through. All right, so it says calcium hydroxide is commonly known as agricultural lime and is used to adjust the soil pH. Before the lime was added to a field, the soil pH was 5. After the lime was added, the soil underwent a 1,000-fold decrease in H plus ion concentration. Okay, so we started at a pH of 5, and there's a this is very important right here, 1,000-fold decrease in H plus ion concentration. So that means if it's decreasing H plus ions, that means it's going to get more basic. That means the pH is going to go up. Okay, so that's good to just kind of know. So if you get an answer that's below that, you're wrong. So first question, yep. What is the new pH of the soil in the field? Okay, so if we're starting at a pH of 5, right, and we have a 1,000-fold decrease in H plus ion concentration, we're going to be going up the scale. So we're going to be going either 6 to 7 or 8 or 9. We're going that direction. Now, how many steps do we go? Look at the number of zeros. There are 3 zeros. That means we're moving 3 steps up the pH scale. Okay? So, and by up, I mean the number gets bigger. Okay? So, 3 steps up would be 5. 1 step is 6. 2 steps is 7. 3 steps is 8. Okay, so the new pH would be 8. All right, and again, that's because a 1,000-fold decrease in H plus. Remember, the less H plus you have, the less acidic and the more basic, and the higher numbers mean more basic. Okay, and we went up 3 because there's 3 zeros. All right, that's what tells us. So if it was 10 times, it'd be 1 step. 100 times is 2 steps. 1,000 times is 3 steps. Okay, which acid-base indicator would allow us to distinguish between soil samples from before and after the calcium hydroxide was added? So we need to distinguish between a pH of 5 and a pH of 8. Okay, so we're going 5 to 8. So what we want is an indicator that is 2 different colors, one color when it's a pH of 5 and a different color when it's a pH of 8. All right, so let's go back to our indicators here. So a pH of 5 would be yellow here, and a pH of 8 would also be yellow, so not that one. A pH of 5 would be yellow here, and a pH of 8 would be blue. So this would work. Check. That's supposed to be a check mark. Okay. Hopefully you're listening and not just watching. A pH of 5 would be, and for phenolphthalein, would be colorless. And a pH of 8 would also be colorless, so not that one. A pH of 5 would be red for litmus paper, and a pH of 8, well, this is not the best indicator. This would probably still work because it's so close to the end of the range. You'd probably be able to tell. The pH of 8 would be pretty much entirely blue. So you could use litmus paper. I'm not going to write anything because it's not the best choice. So far, our best choice is this, right? Try this one. A pH of 5 would be blue. A pH of 8 would be blue, so definitely not this one, right? 5 and 8 are both on this side of the scale. A pH of 5 would be yellow, and a pH of 8 would also be yellow here, so not that one. So bromthymol blue is the best because a pH of 5 would definitely just be yellow, and a pH of 8 would be on this side of the range and definitely be blue. That's the best one. Litmus paper probably would work. pH of 5 would be red, and a pH of 8 would be almost all the way blue. So this is the best choice. I would accept this as an answer as well. Okay, So that's it for this lesson. Definitely replay anything if you need to hear it. I'm going to go on to the challenge question now. Obviously not required, so if you want to try the challenge question, go ahead and pause and I'll go through it.